Industrial conveyor belts that run empty between production batches drain enormous amounts of power. To cut down on this energy waste, we need to design a smart logic system that knows exactly when it's safe to power down a line. We are going to build this for a typical transfer setup: 4 loading conveyors that feed into 2 buffer conveyors, which all merge onto a single receiving belt. To know what is happening on the belts, the system relies on 10 photoelectric sensors. We have 4 loading sensors at the entry points and 6 buffer sensors distributed across the merging and receiving zones. Driving this process are 7 independent motors. Each one is protected by a motor protection circuit breaker, or MPCB, which physically cuts power if a mechanical jam causes an overcurrent. Our objective is to program a sequence that puts the entire system to sleep. But it will only execute if 3 rigid conditions are met. There must be a full 60-second gap in loading, every single belt must be completely empty, and the health of all 7 motors must be verified. Relying on a timer alone is dangerous. A timer might expire while a product is halfway down the line, causing a massive pileup when the next batch starts. By linking a time delay directly to physical hardware checks, we eliminate mid-transit jams, while still cutting energy use to the absolute minimum. To translate this physical machinery into logic, we map everything onto an electrical schematic. The controller for our operation is a Siemens S7-1200 PLC. All 10 photoelectric sensors are wired directly into the PLC's input block. We assign these devices to the digital addresses starting at I0.0 and running sequentially down to I1.1. Next, we wire the normally open auxiliary contacts from all 7 MPCBs into the remaining inputs, filling addresses I1.2 through I2.0. These normally open contacts act as a physical safety boundary. Under normal operation, they're held closed. If a motor overloads, the mechanical breaker trips, the contact immediately snaps open, the 24-volt signal at input I1.2 drops, and the PLC instantly registers an alarm state. Software logic can have bugs, and network communications can lag. Routing hardwired physical limit switches directly into the controller's inputs creates an absolute safety layer that code alone cannot bypass. With our inputs assigned, we write the program in TIA Portal. We build Network 1 to handle our 60-second idle rule. We place an on-delay timer, or TON, and set its preset value to 60 seconds. To trigger it, we wire the 4 loading sensors in series using normally closed instructions, spanning addresses I0.0 to I0.3. Because these instructions are normally closed, power flows through them as long as the physical sensors detect nothing. The timer counts up in the background. If a single product breaks a sensor beam, the corresponding contact opens, cuts the power flow, and resets the timer to 0. The timer handles the idle period. But how do you ensure all 10 sensors across the entire facility are completely clear before cutting power to the motors, so you don't leave a product stranded mid-belt? We solve this in Network 2. We take the timer's completion bit, T1.Q, and place it in series with 10 normally closed contacts, 1 for every single sensor in the system, feeding into a memory coil, M0.0. This memory bit acts as our system empty flag. It can only energize if the timer has finished its 60-second countdown, and simultaneously, no products are blocking any of the 10 sensors. If we only relied on the timer, a bottleneck in the buffer zone could result in a belt shutting off while fully loaded. Demanding an absolute physical clearance check alongside the time delay removes that risk entirely. Let's watch this logic execute during a live shutdown sequence. The upstream loading machines finish their batch and stop feeding the line. Without new products hitting the entry sensors, the T1 timer begins counting up. A minute passes. The timer finishes and sends power to Network 2. However, there is still one final product making its way down the line. It is currently passing buffer sensor 5, which keeps the I1.0 contact open and blocks the logic from completing the circuit. The moment that last product clears the tail end of the receiving belt, the sensor beam reconnects. The I1.0 contact closes in our logic, the system empty coil energizes, and it drops out the run latches for all motor outputs in Network 3. Breaking this run coil immediately triggers the Safe Torque Off, or STO function on the motor drives. Power is electronically removed from the drive units, allowing the entire multi-belt system to gracefully coast to a stop. Designing a smart power down sequence comes down to 3 rules. Time the idle gaps with on-delay timers, verify physical clearance with series-wired sensor logic, and protect the machinery by routing hardware breakers directly into the controller. When you rigorously combine condition-based timing with absolute physical verification, you build automation logic that maximizes efficiency without compromising the safety of the line.
Thanks for watching and grow every day with just a bit of information. Like, share, and subscribe for more content and learning.